In this video, we'll solve one more problem related to Lamis theorem. It is a problem number 3 here. Uh, uh, Similarly, previous first and second problem also solved with respect to some of the bulb and related to string equation, string problems here. These are all application oriented problems here. Now we'll go for the third problem here. Okay. First we'll read the problem here. Also, he's given the figure here. Okay. If a finite string is there, a b c d e. This is a b c d e, one string is there. Okay, whose extremity a is fixed. Its a point is fixed here. Okay, extremity a is fixed. Has weights w1 and w2 attached to it at b and c. So w1 and w2 is attached at b and c. w1 is attached at b, w1 is attached at b point, and w2 is attached at c point. There are two weights. He is attached at b and c, and the one point, the extremity a is fixed. The extremity a is fixed here. Okay, this is the data. Next, it passes around a small smooth peg at d. The passes around at small smooth peg at d here. It means after that, after C, it is passes through a small smooth peg at D here. It is just like the rotary type. It is just like a rotary type at D here. This is one point he is given. At D, carrying a weight of 40 kgf. It is carrying a weight of 40 kgf. It will carry a weight of 40 kgf at point E, at the free end E, at the free end E, as shown in figure. Okay, so it has a string. One point is extremity it is fixed at point A, and at point B and C there are two loads, W1 and W2. And next one is, the next point is it is attached at a smooth peg. It is just like a rotary type. Okay. Next, there you attach the load of 40 kgf at point E. At point E. Okay. Up to here, shown in figure. If in the position of equilibrium, BC is horizontal. This is exactly horizontal. BC is horizontal, and AB and CD makes 150 degree and 120 degree with BC. Makes 150 degree and 120 degree with BC here. It means the AB makes 150 degree with BC, and CD makes 120 degree with BC. Okay. So AB makes 150 degree with horizontal. Also, the CD makes 120 degree with horizontal BC. This is in equilibrium condition. Okay, that is given. When it is exactly horizontal, BC is horizontal, and these two should be 150 and 120, then the string will be in equilibrium condition. That is the point he is given here. What you have to find out? Find tensions in the portions AB, BC and CD. You have to find out the tensions in the portions AB, BC and CD. First AB, BC and CD, how much is there. Next, second point, magnitude of W1 and W2. You have to find out weight 1 is how much, weight 2 is how much here. Okay. So this is how the problem he is given here. Just I'll note down here the data. What data he is given here? The load at E, that is load at E equal to 40 kgf. He is given. Right? That is one data he is given here. Next, what we'll do, for the convenience purpose, we will split the whole the diagram into two parts, and we will analyze one by one, so that it is easy to find out the unknown values here. Okay. What we'll do, first we'll split A, B, C is one portion. Next, B, C, D is one portion. One thing I want to tell that first we'll write that the split for convenience. Split the diagram into two parts. Okay, we will split two parts here. Next point is, what that next point? We will he is asking the tensions in the portion AB, BC and CD. We will write it, the T of AB equal to tension in portion AB. Just we'll give some notation. This is T of AB. Okay. Similarly, T of BC. T of BC is tension in portion BC. In portion BC here. This will be T of BC. We can give it here. Okay. Next, the point is T of CD. T of CD is equal to T of DE. The tension in the CD, this I give it this of T of CD is equal to T of DE. That will be equal to 40 kgf. Can I write like this? Because whatever you are pulling the 40 kgf, the tension is applied on to the portion CD here. So that's why whatever the tension is there, that is equal to in this portion here. So that I write T of CD equal to T of tension in DE, that will be equal to 40 kgf. It will apply on the both portion, it will be same magnitude. Okay, I will write T of CD, tension at CD equal to tension at DE. That will be equal to 40 kgf. 40 kgf. This is the notations we just mark. Okay. So what we have to find out? T of AB, T of BC, and T of CD. That will be equal to T of CD already is there. Okay. Next, W1 and W2 we have to find out here. Okay. Now first we will go for the splitting here. Okay. Split the given diagram into two parts. Okay. First I go through with this part here, second part. You can split both, but first we will split into the second part. This portion, okay, and this portion. Okay. How it looks like here? First T of BC, like this it is there, horizontal. Then this portion, and this is W2, right? This is W2. And the angle, what is this one here? This is BC, B, C, and this is D. And this is T of CD equal to how much is there? 40 kgf. 40 kgf. Okay. And this is the portion here. And this is T of BC, right? This is T of BC. From this we can find out, we will get, apply the Lamis theorem, we will get T of BC and W2. The two values we will get here. How about the tensions here? Tension, it is pulling in this direction, and this will be in this direction, and this will be in downward will be in the downward direction here, weight, because of the weight here. Okay. Now we will write the angles here. Already he is given the angle BCD is 120 degree. This is already 120 degree. 120 degree. Okay. Next, this is how much? 90 degree. This is exactly horizontal, because BC is horizontal. BC is horizontal and W2 is vertical. So this is, can I write it 90 degree? This is 90 degree here. Okay. Then remaining, how we'll calculate here? Next, this will be 150 degree, because this is 120. Now how about this one here? This is 180. Here this is 60 degree, right? 180 minus 120 is 60 degree. 60 degree, and this is 90 degree. This is 90 degree. Total 150 degree. Okay. This is 150 degree. Can I write directly the 150 degree here from here? Because this one is 60 plus 90. 60 plus 90. This will be how much? 150 degree. 150 degrees here. 120 plus 60. This is 180, right? This is 60 plus 90. 150. 150 degree. Okay. Now apply the Lamis theorem here. Apply Lamis theorem. What Lamis theorem? How it will tell us? First we will go tension of BC divided by sine of opposite the angle between the other two forces. How much is there? Sine of 150. Sine 50. 150 equal to, now W2 divided by sine of 120. The angle between this is 120, equal to, one more force is T of CD. T of CD equal to, already it is there. Can I substitute 40? 40 directly I will substitute here. 40 divided by the sine of how much is there? 90 degree. Sine of 90 degree here, right? Now take this and this value and you can find out the tension in BC. Take this and this value and you can find out the W2. That is T of BC divided by sine of 150 equal to 40 divided by sine 90 is 1, right? Sine 90 is 1. Therefore, T of BC equal to sine of 150 into 40 into 40. Substitute the simplify and calculate here. That is T of BC will get 20 kgf. 20 kgf. This is T of BC. So we found one tension here, right? The tension in the BC, string BC is 20 kgf. 20 kgf. We already calculated. Now equate these two for weight 2, W2. That is W2 divided by sine of 120 equal to 40 divided by sine of 90. That is 1. Therefore, W2 equal to sine of 120 into 40, right? To 40. So, therefore, simplify and calculate the weight 2. You will get here 34.64 kg. 34.64 kgf. This is W2. So, we found two unknown values now. That is the weight 2 equal to 34.64 kgf. We found the string in the BC and we found the load in the W2. Now remaining W1 and tension in the AB, right? These two we have to find out. For this one, go for the next split half diagram. ABC, same apply like this. Okay. Now we will go for the second diagram. Just note down here the AB is like this, one is horizontal, BC is like this, and one more is W1. This is A, this is B, and this is C here, right? This is T of BC. Already we calculated. T of BC is how much is there? Already we are calculated here 20 kgf, right? 20 kgf. And W1, and how about this one? T of AB, tension of in AB, string AB. So now apply the directions. Direction is it will be pulling in this direction, and this will be pulling in this direction. Okay. So this is how the directions here. Now calculate the angles. How will you calculate the angle? So he is given already. This is 150. Angle ABC is 150. ABC is this angle already he is given 150. Okay. Since this is horizontal, this is vertical. This will be 90 degree, right? This will be 90 degree. Okay. And how about this here? This is 180 degree. This 180 minus 150 is how much? This is 30, right? This is 30, and this is how much? This will be 90. So totally how much you will get from this to this angle? This is 90 plus 30, 120 degree. So one is 90, one is 50, and one is 120 degree, right? That is the angles between these these three forces. Now apply the same Lamis theorem. First apply T of AB, tension in the string AB, divided by sine of 150, right? No, opposite to this one, 90. This force opposite is sine of 90, equal to, now go for W1 divided by sine of, opposite to this one is 150 degree, right? 150 degree. Next, T of BC equal, we already know T of BC. Can I write it directly? 20? It is 20 kgf. 20 divided by the 120 degree, sine of 120 degree, right? Sine of 120 degree. Okay, now equate this and this, you will get the tension in string AB. Equate this and this equation, you will get the weight of W1. Write the tension in AB divided by sine of 90 is 1, equal to 20 divided by sine of 120, right? Therefore, tension in AB equal to how much we'll get, that is 20 divided by sine of 120. This will be equal to how much we'll get here. The tension in AB is 23.1 kgf. After simplify, 23.1 kgf. This is tension in AB. Where is tension in AB? This here in this. This will be equal to 23.1 kgf. We found. Now we have to calculate the load W1. Again equate. Which one? This and this here. That is these two equation. W1 divided by sine of 150 equal to 20 divided by sine of 120. Therefore W1 equal to how much we'll get here? That is 20 into sine of 150 divided by sine of 120. Therefore W1. Simplify and calculate. How much we'll get here? Simply after simplification we'll get 11.55 Newton kgf. This kgf here. Okay. So where is W1? This will be equal to 11.55 kgf. So in this way you have to split the diagram into two. If number of the points is given, it is very easy to calculate by using the Lames theorem. Okay, three forces you have to segregate and find out the unknown values. Now see, he's asked tension in AB, we found 23.1 kgf. He asked the tension in horizontal string BC, it is 20 kgf, and tension string CD already it is equal to 40 because of the load. This is there. Now weight 1 whatever we are attached is 11.55 kgf and weight 2 is 34.64 kgf. This way it is very easy to calculate by using the Lames theorem. Okay.